In this video, we're going to see tunnel diode, which is also known as Isaki diode. It is known as Isaki diode after its inventor, Leo Isaki, who invented it in 1957 August. Isaki received the Nobel Prize in Physics jointly with Brian Josephson for discovering the electron tunneling effect used in these diodes, which are tunnel diodes. To start understanding how a tunnel diode behaves, we should look at how it looks, okay, in terms of doping and energy band diagram. So to start with, let us consider two pieces of semiconductor crystalline materials, okay. One is doped very heavily with p-type dopant, okay, and the other is heavily doped with n-type dopant. Okay, in that case, when I say heavily doped, I mark it P plus. Actually, double plus you can notate because it is the very heavily doped. Okay, so this makes the difference between any other diode to tunnel diodes. In this case, both the sides are heavily doped, and if you look at its band diagram, it's quite interesting. Okay, now let us see how it looks. Suppose take this is the band diagram. Okay, this is energy band gap for this material, and we are assuming both are of the same material doped with different kinds of dopants. Okay, so Eg will be same for both. And now, and this is a special case anyways, but we'll see. Okay, so this is Ec, and even here Ec. Ec is bottom of the conduction band, and Ev is the top of the valence band. Now when P, this material is doped heavily with acceptor impurity or P impurity, in this case very heavily doped, the Fermi level in this case, when this material becomes degenerated, when it is heavily doped, the Fermi level will be below the top of the valence band, which is EF here. Okay, in this n-type very heavily doped donor impurity, this material, the EF will be above the conduction band. Okay, and here I'm exaggerating the differences here, but usually they'll be close enough. Okay, in order to understand, I'm just exaggerating the difference between ECEF and EVEF. Now when we combine these two and have an open circuit diode, okay, to say here tunnel diode, in that case we should have the Fermi level constant throughout the throughout the tunnel diode, because the current flowing through an open circuit diode should be 0. That happens when EF is constant throughout the material, and we assume here they are uniformly doped. Okay, now if we keep them, if it is together formed with P plus and N plus, the semiconductor material looks like this. Okay, one is P plus and the other is N plus. Okay, this is a metallurgical junction where they're joined kind of. Okay, now if we look at the band diagram, okay, the band diagram I'm going to draw a little bigger to understand it better. Okay, this is how the band diagram looks for this heavily doped P and N diode. Okay, here it is tunnel diode. The striking point to note here is the depletion width, or you can call here the transition region, is going to be very thin when both sides are heavily doped, and usually the order of magnitude of the width will be in terms of few angstroms. Okay, angstrom is like 10 power minus 10 meters, right? So you'll be having a width of this much. And there are two things to note here. One is heavily doping, okay, and the other is depletion width being very low, okay, in terms of angstroms. These are very two important points which we'll be using to refer tunnel diode. Okay, now next we'll see the operation of this tunnel diode when it is forward biased and when it is reverse biased. And the symbol for tunnel or Isaki diode is like this. Okay, just these two, okay, lines which differentiate them from a representation of a normal PN junction diode. And anyways, this side is P and this side is N, which represents the current direction when it is forward biased. Okay, so let us see how this tunnel diode behaves in forward bias. Forward bias is when you apply positive potential with respect to this terminal to this tunnel diode. To say simply, positive to the P side material and negative to the N side material, we say this is forward biased. So now let us look at when the forward bias voltage is, say, 0 volts. How does the energy band diagram look, and what will be the current flowing through this tunnel diode? This is how the band diagram looks, because when you apply zero potential across the tunnel diode, there is effectively no potential which is driving some current to flow through it. So the current flowing through the diode would be zero, and the Fermi level will be constant throughout the tunnel diode, because when you have a Fermi level constant, there won't be any current flow. Okay, so in this case, if we represent the IV characteristics of this particular diode at that particular input voltage or voltage across it, we'll have a point. Let me pick a different color. Okay, a point, take a one. Okay. A point at the origin. Okay, because I'm going to use I in the vertical direction and V in the X direction, as V is independent voltage based on which you'll get current I. That's why we represent in X and Y directions. Okay, so now let us see what will happen if we represent if we apply some positive voltage. Before going to see how it's going to operate, let us see one thing. Okay, that is this, in this side, which is N plus, the below Fermi level, you'll have lot of conduction electrons. Okay, because they are in the conduction band. So there are plenty of electrons here. And if you look at the other side, which is P plus side, okay, in this case we'll have lot of empty spaces here, which means, I mean, unoccupied states in the valence band, which represent the holes in the valence band of this P plus semiconductor. Okay, so we have plenty of electrons here below the Fermi level, and we have plenty of holes above the Fermi level in this P plus. So looking at this, suppose if we apply some positive voltage, say V1 across this tunnel diode. Now how does the energy band diagram look? Let us see. As we know that if we apply negative potential towards the N side, the overall energy of this increases. So the Fermi level at this side and the energy whole diagram moves little up compared to P side, where you are applying positive potential. So what happens is the Fermi level at P side will be slightly lower, okay, if you see, compared to the Fermi level at the N side, and the distance between these two will be equal to the voltage applied across the diode. Okay, so this distance I'm going to name it as V1. Okay, now let us draw the remaining diagram, the band diagram here. I've just exaggerated these regions where there are plenty amount of electrons here in this N side, and there are lot of holes present here. Okay, in order to make it more understandable. Okay, fine. Now let us look at what will be the current flow through this diode when there is a finite amount of voltage applied across the diode in forward bias. Now if you look at it carefully, now we have negative potential here and positive potential here. Now the concept of tunneling comes into picture here. Now let us see what is tunneling actually. We'll make a detailed video on tunneling itself, but for this understanding of tunnel diode, we need two things. Okay, one is, if there is a barrier, okay, for electron to surmount, suppose ideally if you see this electron at this point, if it has to cross this barrier, it has to surmount this whole barrier in front of it. Okay, this is in normal case. But in tunneling, what happens is, if the junction width or the barrier width in terms of space distance is very less, as we have talked before, like it will be in terms of angstroms. So if the width is very less, and if the electron can find a vacant state at the other side of the semiconductor material, okay, which is in this case, there are vacant states in the valence band because of there are holes, right? So which are nothing but absence of electrons in that case. So you have states which can be filled with the electron here. So we have two cases. One is the width should be very less, okay, and the very less, okay, and the second condition is there should be availability of energy states at the other side. So when we have the energy states available at the other side, if you see here in this case, okay, now let me pick this color. Now you can see that the overlap between these two regions is like some proportionality, okay. I'm just specifying it here. So what will happen is these many amount of electrons find these many amount of states of a valence band which are free, which can be filled with electrons, and the width is very low. So what happens is these electrons tend to go through the barrier instead of surmounting it. This is called tunneling. So what happens is these electrons the probability of finding the electrons at the other side is finite now because of the width is low. So we can find these electrons here. So there will be some finite amount of current flow. So if you can represent this in the IV curve here, okay, let me take the IV curve, okay, and we have seen what was the current when the voltage was 0. Now if you see, it increases, okay, for V equals V1, okay, and let's name this as this current as I1, okay. Now if we increase the forward bias voltage, okay, say V equals V2, okay, now let me pull this down. In this case, when you apply say voltage V2, then suppose there is a condition where this overlap of this electron states here to the other side hole states, if they exactly match each other, and if they by using the tunneling concept, you can say that these all electrons can flow to the other side by tunneling phenomena. So what happens is you'll have a current flow through it. So that current flow, if you mark it as for V equals to V2, you have a current which will be greater than I1 for sure, because there are more number of electrons now which can be found at the other side, because there are more vacant states at the other side. So this current, you can take it as I2 for the corresponding V2. Now suppose if we start increasing this voltage to say V3, what will happen? Now in that case, what happens is, if you look at the same diagram and recreate it below, okay, with the corresponding applied voltage, what will happen is, in this case, if you see the electron energy states in the n side region to hole energy states in the p plus region, if you look at the overlap between them, if you see the overlap, okay, from this, the overlap has reduced compared to the previous one, okay. If you see sequentially, what happens is, in this one there was some overlap region which is little, and it started increasing when you increase the voltage. When you further increase the voltage, it has decreased. It's because of the basic reason of the bands being relatively moving in the opposite direction to each other. So the overlap region decreases. As a result, you can predict if we increase the voltage beyond that point V2, okay. So now suppose say we have V3. Now the current that will be flowing through the diode would have reduced, and it will be definitely less than I2, okay. So we'll have a case where the current here is I3, which will be less than I2, right? So let us see if we increase voltage even beyond V3 and go all the way in such a way that there is no overlap region between these two energy states, okay. So in that case, what will happen? Let me go to the next slide and explain that. In this case, when we apply V4, which is greater than V3, what happens is, if there is, now we have run out of the overlap region between these two, okay. So in that case, now it looks like a normal diode where these electrons have to surmount the barrier and go through it in order to find themselves at the other side, okay. So now it looks like a normal diode, right? So what happens is, if you look at the characteristics now, Okay, we have crossed V1, V2, V3, and now when we look at V4, now the current will be very less, okay, just after crossing. And if you go on increasing the voltage now, it starts increasing just like a diode characteristics. So now if you look at the summary of it, okay, if you consider all this V1, V2, V3, V4 and so on, let us draw the characteristics how they look, okay, under forward bias. So now we saw when V input was 0, the current was 0, right? So no confusions here. Now when we applied V1, the overlap region between those two energy ranges was some finite and it was not maximum. So we saw some I1 current, okay? And then we saw some condition where V2 was in such a way that the overlap between the two energy levels, the electron energy levels and hole energy levels, were more. So in that case we had I2, okay, for corresponding V2. Now we saw one more case where when V3 is applied where the overlap region has reduced, right? That was for V3. And for V4 and going on further, what happens is this current gradually comes down, and after some point it starts behaving like a normal diode with respect to the voltage. So if we connect them and see how this thing actually behaves, okay, it goes like this, okay, and it starts having a curve like this, okay. It exponentially increases just like a normal diode characteristics. Now if you look at this and try to correlate with what we have seen with the normal diode characteristics, okay, if you see, it will be like this, okay. It is overlapping with normal diode characteristics like this. So now there are some important parameters to note here, okay. The point at which you will have highest current, okay, for corresponding voltage is known as IP. The current corresponding value will be IP. This is called peak current, and the corresponding voltage is called peak voltage. And if you see here, it looks like a valley, right? The current decreases and then increases. It looks like a valley. So the point at which it actually goes to a lower value and then starts increasing, that point we call that current as valley current, and the corresponding voltage as valley voltage, okay. Now the most important application of these tunnel diodes are based on the negative resistivity or negative resistance of these tunnel diode which offers, okay. If you see here, when you increase the voltage, current increases, whereas in this region where V is in between VP and VV, you'll have current changing from higher value to lower value, okay. There you have, if you take a derivative at this point, you'll have negative resistivity, okay, or negative resistance. So this is where these materials or these tunnel diodes are used most, and the tunnel diodes can operate at a very high frequency of operation into gigahertz. So in microwave applications, these tunnel diodes are used mostly for oscillators because it has negative resistivity or resistance. Now let us look at how this tunnel diode behaves when it is reverse biased. Reverse bias is when we apply negative potential to the P side and positive potential to the N side. Now suppose we apply 0 volts, and we have seen this energy band diagram even before, okay. When you apply 0 volts, this is how the energy band diagram looks like, and this is how the current IV characteristics look, and the current flowing through it will be 0 because EF is constant throughout the tunnel diode. Now let us apply some negative voltage across this PN diode, okay. So let me take this, PN diode. In this case it's tunnel diode, okay. So now I'm going to apply reverse bias, and let me say this is like VR1, okay, reverse bias voltage, some finite value. Now how does this energy band diagram look like? As we have applied negative sign at the P side, the overall average electron energy at the P side increases, so the energy band diagram at P side increases with respect to the N side. So now if you look at the quasi-Fermi level at the P side will be at a higher level, okay, and if you look at the energy states of the holes there are represented in this yellow color, okay, and the electron energy states which are filled and there are electrons here in n side are represented with blue color. Now if you see here, what happens is you have a lot of these minority electrons here, okay, minority electrons, and we have seen what is tunneling, right, before when we discussed the forward biasing of the tunnel diode. Now if we consider the electrons here, and there are vacant states here above this quasi-Fermi level EFN, right? So these electrons, when you consider the width of the junction width, okay, even though you reverse biased it, the junction width increase will be very negligible, okay. So even then the depletion width will be in terms of angstroms, and there are empty states at the other side where the electrons can tunnel through instead of surmounting the barrier, or in this case a different phenomenon, okay. So these electrons will tunnel through and there will be a current flow. Unlike any other diodes, in reverse bias it doesn't allow current flow, but tunnel diodes do allow. So what happens is, if you start increasing the reverse voltage across it, the difference between the EFN and EFP here will be increasing, and these minority electrons can find themselves at the other side, and there will be current flow, and that current flow will also increase with respect to the reverse bias voltage increase. So what happens is, if we can draw the figure here for the reverse bias and how the current flow through, okay, so you'll have current characteristics something linear, okay, fine. As you increase the voltage in reverse bias, the current will also keep on increasing, okay, in the reverse direction, okay. As we are plotting, taking the reference direction as this, so that's why we take the current which is flowing in the other direction as negative, okay, and the reference voltage is positive negative, and the voltage which you actually apply is in reverse direction, that's why it is in negative direction. So this is how the characteristics of the tunnel diode looks when it is reverse biased. You can clump both of them and see how the characteristics look. So let me draw the forward characteristics along with this, okay. So this is how it'll look, okay, it'll be kind of straight, okay, and you can reiterate, okay, or say along with me, this point is known as valley voltage. Oops, sorry, what is it? It's peak voltage, and this current is known as peak current, and this is valley voltage, and the current corresponding to this is known as valley current, okay. One of the striking factors of tunnel diodes is its longevity, okay. These devices, which are manufactured in say 1957, which when Isaki has invented them, those diodes still do work, okay. So the longevity of these diodes are very high. The tunnel diodes are very reliable and they operate for a very long time, okay. Thanks a lot for watching.